This video is sponsored by UPDF. Imagine a scientist dropping a silvery chunk of metal into a tank of water. For a split second, nothing happens. Then boom! A flash of light and a burst of flames erupt as the metal explodes, shattering the container. This isn't a scene from a sci-fi movie, it's a real chemical element in action. That volatile metal I'm talking about is rubidium. Rubidium is an element notorious for its violent behavior when provoked by water or even air. It's so reactive that it can ignite spontaneously just by being exposed to moisture in the air. With such an explosive personality, one can't help but ask, is rubidium the most dangerous element? Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, hype, subscribe and hit the notification bell so you will never have to miss another episode. Also make sure to fill in the poll in the post section of the channel for next week, as we will be discussing another element again. Now, inside this cube, rubidium looks deceptively calm. It appears as a soft silvery metal, often slightly dull rather than mirror shiny, sometimes with faint gray or yellowish patches from minimal oxidation. The cube itself acts like a protective prison in this case, isolating the rubidium from air and moisture that would instantly trigger a violent reaction. Now, frozen in place, the metal may look almost wax-like, sometimes irregular in shape, as if it were gently pressed rather than machined. Well, it seems in this case as if it just turned from liquid to solid. And with its low melting point, that could have been the case. Now, I seriously do not know why we would even discuss this after the intro, but can you lick it? Well, no, absolutely not. And the periodic leaking table is warning you here. Licking rubidium would be extremely dangerous and potentially life-threatening. Rubidium is one of the most reactive metals known, and the moment it comes into contact with water, it reacts violently. Your mouth and tongue are full of moisture, so instead of tasting the metal, you would instantly trigger a chemical reaction. Rubidium in this case would rapidly release heat, produce hydrogen gas that could ignite and form rubidium hydroxide, a highly corrosive substance similar to industrial lye. This could cause severe chemical burns to the tongue and mouth, intense pain, rapid tissue damage, dangerous swelling, and even fire inside your mouth. Even an extremely small amount could cause serious injury. This is why rubidium is always stored under oil or inert gas and only handled by trained professionals using protective equipment. Rubidium is fascinating to learn about, but it is an element that should never come into contact with the human body. The tale of rubidium's discovery is the tale of the glow of colored flames. It was in the year 1861 in Heidelberg, Germany, where two chemists, Robert Bunsen and Gustav Kirchhoff, were pioneers of the new technique called flame spectroscopy, using the colors of flames to detect elements. When certain chemical salts are put into a flame, they produce distinctive colors. Bunsen, famous for the Bunsen burner, Kirchhoff had recently used this method to discover a new element called cesium by its sky blue flame. Soon after, they examined a mineral called lepidolite, and this is a piece from our own collection, a purple-colored mica rock, and noticed bright red streaks in the spectrum of its flame. Those vivid red spectral lines did not match any known element. It was a clear sign they'd found something new. In fact, this was only the second element ever to discovered with the aid of spectroscopy. Bunsen and Kirchhoff decided to name this new element rubidium. The name comes from the Latin word rubidus, meaning deep red. They chose it to honor the prominent deep red color of its spectral lines. Essentially, rubidium announced its existence with a red signature in the flames. It's a bit poetic that an element so associated with fire and explosive reactions was named after the color of firelight it emits. Interestingly, rubidium's actually flame color test, when you burn a bit of it, is usually described as a pale purple-violet, very similar to its cousin potassium. But those specific dark red bands in the spectroscope were unique, and rubidium proudly carries the meaning deep red to this day. The discovery process was painstaking. Rubidium was present only in tiny amounts of lepidolite ore. Bunsen and Kirchhoff had to process an enormous quantity of the mineral to isolate rubidium compounds. Historical records describe how they started with 150 kilograms of lepidolite ore just to extract a small sample of rubidium salt for analysis. To separate rubidium from the more common element potassium, which has a similar chemistry, they performed repeated fractional crystallization, essentially multiple rounds of slow crystal formation to gradually concentrate the rubidium. After a laborious process, they ended up with only about 0.5 grams of rubidium chloride. From all that rock, not stopping there, Bunsen and Kirchhoff also turned to mineral spring water as a source. They evaporated and analyzed 44,000 liters of mineral water, that is roughly the volume of a small swimming pool, to extract additional traces of the new element. From that huge volume, they only got a few grams of rubidium compounds. Now, these numbers give a sense of how scarce and diluted rubidium was in the sources they had, and how determined the scientists were. Keep in mind, at the time, rubidium had no known use. It was scientific curiosity that drove them. Rubidium's identification by flame colors was cutting-edge science in 1861. It marked an early success of spectroscopy, a method that would later become fundamental in chemical analysis and astronomy. In fact, rubidium was discovered just 1 year after the spectroscope itself was invented by those same scientists. Now, this means rubidium holds a special place in history as one of those first elements discovered not by traditional chemistry, like reacting substances or observing weights, but by analyzing light. It was a bold demonstration that looking at an element's light fingerprint could reveal things our eyes and our classic techniques could not see directly. After discovery, the next challenge was obtaining pure rubidium metal itself. Initially, Bunsen attempted to isolate rubidium metal by using electrolysis on molten rubidium salts, a method that worked for isolating some other reactive metals. However, his attempts produced an odd blue-colored material instead of a shiny metal globule. At the time, he thought it might be a compound of rubidium, a subchloride, but we now know that it was likely a colloidal mix of rubidium metal and rubidium salt, basically tiny metal particles suspended, giving a blue appearance. Bunsen didn't give up. He tried a different approach, reducing rubidium tartrate, a rubidium-containing salt of tartric acid, by heating it with carbon. Now, the second attempt succeeded in producing actual rubidium metal, albeit in a very small quantity. The rubidium metal they obtained was extremely reactive and even pyrophoric, meaning it could ignite spontaneously in air. They were able to measure some of its properties like density and melting point, and impressively, their 1860s measurements were very close to the modern values. It wasn't until many years later, decades after Bunsen's work, that larger amounts of rubidium metal were isolated, and credit is often given to the chemist Georges de Hevesy in the early 20th century for first isolating rubidium in a substantial pure form. By then, the scientific understanding of atoms and isotopes had advanced, but Bunsen and Kirchhoff's initial discovery laid the groundwork. So let's take a look at the properties of rubidium. So like we see in the cube, you'd first notice it looks silvery white and metallic. It's extremely soft, so soft that you could cut it with a knife quite easily. In fact, rubidium is even softer than sodium and potassium, which are famously soft metals. Press a knife into rubidium and it would slice smoothly, rather like cutting through a hard wax or a chunk of cheese. Freshly cut rubidium would reveal a bright, shiny surface, but not for long. Almost instantly, that silvery shine would begin to dull. Rubidium oxidizes in air very rapidly, meaning it reacts with oxygen and even with nitrogen and moisture from the atmosphere. Now, within moments, a fresh rubidium surface turns from silvery metallic to a tarnished gray. Leave it out for a bit longer and it might develop coatings of rubidium oxide compounds. Rubidium has some remarkable physical properties. Its melting point is only about 39 degrees Celsius, 102 degrees Fahrenheit, and that is just slightly above normal human body temperature. This means if you held a rubidium ampoule in your hand and warmed it, again, don't actually do this, the metal could start melting into a liquid. On a hot summer day, solid rubidium could become a puddle of liquid metal. There are only a few metals with such low melting points, for example. Mercury is a liquid at room temperature. Cesium melts at around 28 degrees Celsius, and gallium melts around 30 degrees Celsius. Rubidium isn't quite liquid at room temperature, but it's close. Its boiling point is about 688 degrees Celsius, which is relatively low for a metal. By comparison, iron's boiling point is over 2800 degrees Celsius. These low melting and boiling points reflect rubidium's placement on the periodic table. It's a large atom with only a weak hold on its outermost electron, leading to relatively low interatomic binding strength. Rubidium's atomic number is 37. This means each rubidium atom has 37 protons in its nucleus. It lies in the group 1, the alkali metal group, which includes some famous reactive elements like lithium, sodium, and potassium above, rubidium in the group, and cesium and francium below it. Now, all alkali metals have a single electron in their outer shell, and this is the key to their chemistry. With only one valence electron, alkali metals are desperate to give it away. They are highly electropositive. Rubidium is no exception. In fact, it's one of the most electropositive elements known. Now let's talk about the reaction that makes rubidium infamous. It's the reaction with water. When rubidium metal comes into contact with water, H2O, a vigorous chemical reaction happens. The rubidium atoms gives its electron to the water molecules, producing rubidium hydroxide and hydrogen gas. This reaction can be summed up as follows. Now this reaction is exothermic. It releases a lot of heat very quickly, so when rubidium touches water, the hydrogen gas that forms doesn't just bubble harmlessly, it usually ignites immediately, because the heat of the reaction, plus the presence of oxygen in air, causes the hydrogen to catch fire. The result is a rapid explosion, or at least a violent flash. In essence, rubidium throws a fiery tantrum in water. If you've ever seen a piece of sodium or potassium thrown into water, you know they fizz and often burst into flames. Rubidium is significantly more reactive than potassium, so its water reaction is correspondingly more violent. A large chunk of rubidium can cause a real explosion upon hitting water, blasting apart its container and sending scorching alkali solutions flying around. The rubidium hydroxide produced is a strong base, basically a caustic alkaline solution, similar to lye, that can burn skin. So not only do you get fire and shrapnel, you also get a corrosive chemical out of the deal. This is why chemists handle rubidium with extreme caution. Even a small piece can create a dangerous situation. One dramatic difference between rubidium and the lighter alkali metals is density. Rubidium is denser than water, about 1.5 times the density of water. Lithium, sodium, and potassium are all less dense than water, so they float and skitter on the surface when reacting. Rubidium, however, is heavier, so it sinks in water. What's interesting is that as rubidium sinks, it keeps reacting vigorously all around its surface, so the reaction doesn't just stay at the top. It goes through the water until the rubidium is consumed, which happens very, very quickly. Meanwhile, the hydrogen gas bubbles rush upwards and often ignite at the surface. Now, cesium, the next alkali metal, is even denser and famously explodes on contact with water almost instantly. In comparison, rubidium's reaction, while extremely violent, sometimes is described as slightly slower than cesium's. But make no mistake, it's plenty hazardous. The exact explosiveness can depend on how the metal is divided. A fine piece of rubidium dust will react even more quickly, even explosively so, than a single lump, because more surface area is exposed at once. In any case, dropping rubidium in water is the chemistry equivalent of lighting a very short fuse. Rubidium also reacts eagerly with air. If exposed, it will react with oxygen to form rubidium oxide, and with the moisture and oxygen together, it can form peroxides and superoxides. These compounds, like rubidium superoxide, can form a yellow-orange crust on the metal. A dangerous aspect is that these oxide coatings themselves can be unstable. For instance, alkali metal superoxides and peroxides are sometimes shock sensitive. They can detonate if scratched or disturbed after they build up. Now this is analogous for what happens with potassium metal. Old samples of potassium that have formed peroxide crust can be known to explode when someone tries to cut or handle them. Rubidium likely has similar issues, which is why handling of partly oxidized rubidium is a serious risk. But usually chemists are careful to store rubidium properly to avoid this scenario, rather than biochemical. Another surprising aspect of rubidium is that it is slightly radioactive. Rubidium has two natural occurring isotopes, rubidium-85 and rubidium-87. Rubidium-85 is stable, making up about 72% of natural rubidium. Rubidium-87, which accounts for the remaining 28%, is radioactive. It undergoes very slow beta decay. Now the term radioactive here might sound alarming, but rubidium-87's half-life is about 48 billion years, which is more than 3 times the current age of the universe. That means it decays so slowly that it's only barely radioactive. Nevertheless, if you have a sample of rubidium metal, about a quarter of it is rubidium-87, atoms that will once in a blue moon emit a beta particle, essentially an electron. Rubidium might be highly reactive, but it's not a particularly rare element in the Earth's crust. In fact, it's more abundant than some very well-known elements. Estimates put rubidium as roughly as the 23rd most abundant element in the Earth's crust. There's more rubidium in the ground than there is copper, for example, and also more zinc than there is rubidium. This sounds surprising. If it's more common than copper, why don't we hear about rubidium more often then? The reason is that rubidium is widely distributed, but not concentrated. Unlike copper, which can form rich ores that are economically mined, rubidium tends to tag along in small quantities within other minerals. There are no vast rubidium ore veins where rubidium is the main constituent. Instead, rubidium is usually a substitute for other similar elements in minerals. As rubidium atoms are similar in size to potassiums and to some extent to cesiums, it often sneaks into minerals that are mainly potassium or cesium or other alkali metals. One common source of rubidium is the mineral lepidolite, which we mentioned in the context of its discovery. Lepidolite is actually a lithium-rich mica used as an ore of lithium. Within lepidolite, rubidium can replace some of the potassium or lithium in the mineral structure. Lepidolite samples can contain anywhere from 0.3% up to about 3% rubidium oxide by weight. That's not a huge percentage, but it adds up if you process large amounts of the mineral. Another rubidium-bearing mineral is pollucite, which is primarily a cesium ore. Pollucite can carry a few percent of rubidium as an impurity alongside cesium. Other minerals that may contain traces of rubidium include carnallite, a potassium-magnesium chloride found in evaporated deposits, and zinwaldite, another lithium-potassium mica that sounds more like a character from Harry Potter than a mineral. Even the volcanic mineral leucite has rubidium in it. In essence, rubidium's presence is usually as a minor ingredient, substituting for potassium in the crystal lattices of various rocks. Now, because rubidium likes to stick with potassium, even potassium salts and brines can contain some rubidium. For instance, certain natural brine deposits or concentrated salt lake waters that are mined for potassium might have rubidium in the mix. Seawater itself contains rubidium, but extremely diluted on the order of 0.1 to 0.2 milligrams per liter, which is hundreds of times less concentrated than potassium in seawater. So while the oceans hold a lot of rubidium in total, it's too diffuse to extract it practically. Instead, the industrial sources of rubidium have traditionally been those minerals like lepidolite and pollucite, often as a byproduct of mining lithium or cesium. Now, how do we extract rubidium from those sources? The process usually involves separating rubidium from the chemically similar potassium and cesium. One of the classic methods used by Bunsen in the early days is fractional crystallization of mixed alkali metal salts. For example, if you have a mixture of rubidium and cesium and potassium in solution, you can convert them into a form like alum salts or various double salts, where rubidium compound is a little less soluble than potassium's, but maybe more soluble than cesium's. By carefully cooling the solution, certain crystals will form, leaving others in the solution. Repeating this dozens of times can gradually tease apart these elements. Bunsen did this with the chloroplatinate salts. He found rubidium hexachloroplatinate is less soluble in hot water than potassium's equivalent, allowing him to separate rubidium. Modern chemistry has more efficient techniques too. Other processes historically noted are the chlorostenate process and the ferrocyanide process. These are methods that use special precipitating agents to preferentially crystallize out either cesium or rubidium, thus separating them. Details aside, think of it as a clever chemical filter trick to isolate rubidium from its look-alike neighbors. Today, rubidium is still largely obtained as a minor byproduct. Mining operation for cesium, like those extracting pollucite ore, or for lithium, like those processing lepidolite, or other lithium-rich rocks, which sometimes extract rubidium from the mother liquor after the main product is taken out. One of the historically significant sites was at Burnick Lake in Manitoba, Canada, which had a large deposit of pollucite, rich in cesium. That cesium mining also produced rubidium. Another notable find is on the Italian island of Elba, where a mineral called rubicline was identified. Rubicline is essentially a form of potassium feldspar, where a hefty chunk of potassium is replaced by rubidium, reportedly containing up to 17% rubidium. Now, such rich rubidium minerals are extremely rare, hence the name rubicline, honoring rubidium. They aren't mass production sources though, but they show that rubidium can sometimes accumulate under unique geological conditions. Globally, the amount of rubidium produced and used is quite small compared to most industrial metals. Current production of rubidium, mostly in the form of rubidium salts, since the metal itself is usually made only on demand from the salts, is on the order of only a few tons per year, maybe 2 to 4 tons worldwide. And this is tiny. Now, for perspective, humanity produces millions of tons of aluminum and copper each year, and even rare elements like silver or lithium are produced in the thousands or tens of thousands of tons. Rubidium compounds, such as rubidium carbonate, are used in certain specialized glasses. Adding rubidium to glass mixtures can change properties like conductivity or optical characteristics. Now, for example, rubidium carbonate is sometimes used in fiber optic cables or other advanced glass products to reduce electrical conductivity or to modify the glass refractive index. Rubidium isn't a primary ingredient in common glass, like window panes, but in high-end optical components it can play a role. There is also a remarkable rubidium-containing crystal, rubidium silver iodide. This material holds a record for ionic conductivity at room temperature. It conducts electricity via ion movement, as well as some strong acids do. Now, because of that, the rubidium silver iodide has been studied for use in thin film batteries and other electrochemical applications. It's a solid crystal that behaves almost like an electrolyte solution in terms of how easily ions move through it, which is quite fascinating. Now, the deep reds and the vibrant purples produced by rubidium salts find a use in the art of fireworks. Rubidium compounds like rubidium nitrate or rubidium carbonate can be added to pyrotechnic mixtures to give a purple color to the flames. Purple fireworks are often made with a mix of strontium, red, and copper, blue compounds to get a violet hue. But rubidium can also provide a rich purple-red color on its own. It's not the most common coloring agent because rubidium is expensive compared to other salts, but it's used in some specialty fireworks or flares. Rubidium has a history of use in electronics, particularly in older technologies. It has been used as a getter in vacuum tubes. A getter is a material that's placed in a vacuum tube, like old radio tubes or certain scientific apparatus, to absorb any residual gases and maintain the vacuum. Rubidium, like all other alkali metals, readily reacts with stray oxygen or other gases, binding them up. In some cases, a bit of rubidium or a rubidium-containing alloy would be sealed in the tube. When the tube is evacuated and sealed, the rubidium is heated to vaporize it, and it then reacts with leftover gas, coating the inside with a thin layer of metal and effectively removing those gases. This helps keep the vacuum hard, in example very empty, for the device to function properly. Rubidium isn't the only getter material. Barium and others were also used, but it's part of the toolkit. Rubidium also shows up in photocells and photoelectric devices. A photocell is a device that converts light into an electric current, or vice versa. Certain compounds of rubidium and often cesium have the property of being good at emitting electrons when illuminated, the photoelectric effect. One of the coolest uses of rubidium is in timekeeping. Rubidium atomic clocks are extremely precise timekeeping devices that use the element's atomic properties. Rubidium clocks aren't as ultimately precise as the more famous cesium atomic clocks, which define the official second, but they are similar, cheaper, and still very accurate. They might drift only a few milliseconds over many years. They are widely used as secondary frequency standards in telecommunications. For example, the timing for cell phone networks and GPS-based stations often rely on rubidium clocks to ensure synchronization. If you have a GPS receiver or make a phone call, rubidium might be indirectly helping that system keep perfect time. Rubidium has become a star in the world of physics research. In 1995, rubidium atoms were used to achieve something extraordinary: the creation of the Bose-Einstein condensate. Now, this is a state of matter that occurs at ultra-cold temperatures, just a hair above absolute zero, where a dilute gas of certain atoms can occupy the same quantum state and behave like a single superatom. The scientists at Cornell and Wieman used rubidium-87 atoms cooled by lasers and evaporate cooling to achieve this state, a breakthrough that earned a Nobel Prize. Now, a Bose-Einstein condensate is a special state of matter that happens when atoms are cooled down to almost the coldest temperature possible, close to absolute zero. Now, when this happens, the atoms slow down so much that they stop acting like lots of separate tiny particles and start behaving like one single super big particle. It's as if a bunch of kids running around on a playground suddenly froze and all decide to move together in perfect sync, like they were one person. Scientists find this amazing because it let them see strange quantum behavior that are normally hidden in everyday life. Rubidium has found a niche in nuclear medicine. A radioactive isotope, rubidium-82, is used in positron emission tomography, or PET scans, particularly for heart imaging, myocardial perfusion imaging. Rubidium-82 is very short-lived. It has a half-life of only 76 seconds. Now, because it decays so quickly by emitting positrons, the antimatter counterpart of electrons, it's ideal for scanning organs like the heart. It delivers a quick burst of imaging signal and then disappears, minimizing radiation dose. Now, in practice, rubidium-82 is not shipped to hospitals as a vial, since it would decay away within minutes. Instead, hospitals use a strontium-82/rubidium-82 generator. Strontium-82 decays with a longer half-life of 25 days into rubidium-82. So a device containing strontium-82 can produce rubidium-82 on demand, which is then mixed into a saline solution and injected into the patient immediately for a PET scan that reveals blood flow in the heart muscle. Now, if parts of the heart don't take up rubidium, which behaves like potassium and goes wherever blood flows, it indicates poor blood supply or damage, critical information for diagnosing coronary disease. Rubidium-82's fleeting existence is a dramatic contrast to rubidium-87's almost eternal half-life. One is used to peer into a living heart in real time, the other one to date rocks billions of years old. So now the remaining question of the video, is rubidium really the most dangerous element? In terms of chemical reactivity, it's definitely near the top. Rubidium belongs to alkali metals, a group where reactivity increases as you move down the periodic table. Lithium fizzes in water, sodium dances, potassium sparks, but rubidium really explodes. Only cesium is more violent, and francium is so rare and radioactive that it's never been seen reacting in real life. Among elements that can actually be handled, rubidium and cesium are the most extreme. However, danger depends on how you define it. Rubidium is not highly toxic in the way that elements like mercury, lead, or arsenic are. It also isn't dangerously radioactive. Its natural radioactivity is extremely weak compared to elements like plutonium or polonium. Its main trait isn't poisoning or radiation, but fire and explosions. So while rubidium may not be the deadliest element overall, it stands out as one of the most immediately dangerous elements to handle. If danger means most likely to explode, if you make a mistake, rubidium is a top contender. Second to only cesium. Now, rubidium is one of those elements that remind you that science isn't just about ideas on a whiteboard. It's really messy and sometimes explosive. There's the funny part. Even when the chemistry is dramatic, the paperwork is usually worse, because the real struggle for a lot of people isn't the reaction beaker, it's the research papers, lab notes, and PDFs that refuse to cooperate. If you deal with research papers, lab notes, or PDFs that never do what you want, UPDF is a powerful all-in-one PDF editor that works on Mac, Windows, iOS, and Android. And one license works across all your devices. What I love is how fast it is. You can edit text, images, links, add or remove watermarks, and even reorganize pages in seconds. For studying, the reading and annotation modes are great, including eye protection mode, which my eyes really appreciate. But the coolest part is the AI assistant, because with this feature you can actually chat with your PDFs, summarize research papers, translate them, explain confusing sections, turn PDFs into mind maps, or even deep research right inside the app. It also handles OCR, PDF conversion, password protection, redaction, digital signatures, and batch processing. So it's perfect for both students and professionals. Now, the best part is that UPDF costs about 1/6 of Adobe Acrobat and comes with lifetime free updates. And they're rolling out new features almost every month. There's a limited offer right now. Check on the link in the description, and I've also pinned it in the comments. You can download UPDF for free and try it yourself. So, is rubidium the most dangerous element? It depends on your criteria, but it's undeniably a strong candidate for the most reactive metal you'll likely never hold in your hand. In the realm of exploding elements, rubidium ranks near the top. In the end, rubidium stands as a fascinating example of nature's extremes, from its deep red spectral signature hidden in a piece of lepidolite, to a violet flash of its flame, to a nearly invisible role it plays in the infrastructure of our modern world. Rubidium's story is full of surprises. Now, we would like to thank the members that support our channel. Thanks for doing this, we really appreciate you. Now, if you think we missed anything, tell us in the comments, and if you want to know more about another reactive element, take a look at this old video about cesium next.